Welcome back to Mechanical Engineering Made Simple, the podcast that makes you sound intelligent without needing a PhD or therapy.
Or a very expensive legal team, depending on how bad your design fails.
Right, yeah, exactly. So I want you to imagine, just for a second, that you are the lead design engineer on this, highly critical aerospace project.
Okay, no pressure.
Right. You've spent, I don't know, 3 years and maybe $5 million designing this absolutely beautiful, intricate titanium mounting bracket for a satellite component. You've run the finite element analysis models hundreds of times. The color gradients on your computer screen are they're perfect.
A sea of comforting blue.
Yeah, zero stress concentrations. The math is pristine. So you finally send the physical prototype down to the shop floor to be run on a shaker table. You go down to watch the test, fully expecting a victory lap. And within, 45 seconds, your $5 million bracket chatters, cracks, and completely shears in half.
Oh, man.
Your summit drops. You failed. But here is the kicker, and the whole reason we are doing this deep dive today.
Yeah.
Your bracket was perfectly fine. It was the test that lied to you.
Yeah, and honestly, that is, it's the ultimate nightmare scenario for any design engineer. And the scary part is, it happens far more often than anyone in the industry actually wants to admit.
No.
Yeah. There is this massive, incredibly treacherous gulf between the idealized mathematical environment upstairs in the engineering department and the messy, chaotic physical reality down on the shop floor.
Okay, let's unpack this. Because if you are listening to this right now, you are probably someone who wants to avoid those costly, career-damaging mistakes. We're looking at a massive stack of definitive source material on shock and vibration analysis today.
Nah.
Our mission is basically to map out this disconnect. Because on one side, we have the folks who run the math and write the specs. And on the other side, we have the technicians who actually have to mount the sensors, glue the strain gauges, and run the drop tables. And I guess the foundational truth we just have to accept right up front is that the physical world is inherently hostile to pristine CAD models.
It is entirely hostile. I mean, the whole premise of analyzing a structure's vibration assumes that you can accurately measure it in the first place. The design engineer just assumes the data coming back from the shop floor is pure.
Right, it's just numbers on a spreadsheet to them.
Exactly. But the very act of capturing that physical data introduces all these physical variables that completely poison the results if you don't account for them.
Okay, so let's start right there at the actual point of physical contact. So before I can look at a gorgeous graph of resonance frequencies on my monitor, a technician has to physically attach a transducer, an accelerometer, to a piece of metal. But, my brain tells me a sensor is just a passive observer. It's just sitting there listening to the vibration. But the sources are telling me that is a fundamental misunderstanding of the physics.
It is a profound misunderstanding. The sensor, and crucially, the mounting bracket used to hold the sensor, are not passive observers at all. They're dynamic systems in their own right. Every physical object has mass, it has stiffness, and it has its own natural frequency.
Okay.
So when the shop technician attaches a mounting bracket and a transducer to your titanium satellite part, they are no longer testing your part.
Wait, what are they testing?
They are testing a brand new combined mechanical system consisting of the part plus the bracket plus the sensor.
Oh, wow. So by trying to measure the structure, I have essentially built a completely new structure. But, how much of a difference does a tiny little bracket actually make?
Right.
We're talking about a piece of hardware that fits in the palm of your hand.
It can completely rewrite your data.
Yeah.
What's fascinating here is how something so small just dominates the math. The sources highlight this beautiful, terrifying example. Let's say the technician decides the standard steel mounting bracket is too heavy, or maybe, they just don't have one nearby.
Sure, yeah. Shop floor reality.
Right. So they swap it out for a bracket made of phenolic plastic. It has the exact same dimensions, the same geometry. But just by changing the material from steel to plastic, you actually have the resonance frequency of the mounting system.
Wait, cut the frequency in half.
Yep.
Literally 50%, just by swapping the metal for plastic. Explain the physics of that to me. Why does the material change the frequency so drastically?
Think about a weight bouncing on the end of a spring. The speed at which it bounces its natural frequency depends on two things. It depends on the mass of the weight and the stiffness of the spring.
Right, okay.
A bracket is effectively a very short, very stiff spring connecting the sensor to the structure. Steel has a very high modulus of elasticity, right? It is incredibly stiff.
Yeah.
Phenolic plastic is much softer. It is a weaker spring.
Yeah.
If you put the exact same sensor on a weaker spring, it is going to bounce slower. The frequency drops.
Oh, geez. So the data acquisition system is going to record a massive resonance at, say, I don't know, 5,000 hertz. The engineer sitting upstairs is going to panic, thinking their titanium part has a fatal flaw at 5,000 hertz. But that flaw doesn't even exist.
It doesn't exist at all. It's just the plastic bracket jiggling.
That's wild.
And, it goes further than that. Let's say they stick with the steel bracket, but they change how they attach it to the structure. The design might call for a mechanical screw mount, but the technician decides they don't want to drill a hole in the pristine prototype.
Because it's a $5 million part.
Exactly. So they use a high-strength epoxy resin adhesive bond instead.
Okay, let me play devil's advocate here for a second.
Yeah.
Glue is strong. Modern epoxies are practically indestructible. Surely that doesn't change the dynamic profile of the test.
Oh, it changes it significantly. The epoxy bond typically creates a much larger, more uniform area of contact between the bracket and the structure compared to just a single screw, which, only contacts at the threads in the base.
Okay, I see where you're going.
Yeah, the epoxy massively increases the stiffness of the connection. So going back to our spring analogy, you just made the spring way stiffer, the resonance frequency shoots up, the data is altered all over again.
That feels incredibly counterintuitive. The tool you are using to measure the object fundamentally alters the object. It kind of reminds me of trying to measure the speed of a tiny, delicate paper boat floating down a stream, and your method of measuring it is to drop a massive 5-pound GPS tracking brick right into the center of the boat.
Yes. That is a perfect analogy for the concept of mass loading. And mass loading is the absolute bane of vibration testing on lightweight structures. If you take a thin aluminum panel and you attach a heavy transducer to it, you are the GPS brick in the paper boat.
You're sinking it.
You've added localized mass to the panel without adding any stiffness. What happens to our weight on the spring when we add more weight?
The balancing slows down. The natural frequency drops.
Exactly. The engineer gets the report back, and the data shows the panel resonating at a dangerously low frequency. They might spend weeks redesigning the panel, adding ribs, adding weight, trying to stiffen it up to push that frequency higher. But the panel was perfectly fine to begin with.
They're literally redesigning the part to survive the weight of the sensor.
Exactly.
The tail is completely wagging the dog here.
Yeah.
Okay, so we have the bracket lying to us. We have the weight of the sensor lying to us. But there is a detail in the source material that sounds straight out of a science fiction novel, and it has to do with the cables.
Well, the cables, yes.
The wires connecting the sensor back to the computer? Triboelectricity. What in the world is a triboelectric effect, and how is a piece of wire ruining my $5 million test?
Triboelectricity is essentially cable noise generation, and it is a silent killer of accurate data. Inside a typical measurement cable, like a standard coaxial cable, you have a central conductor wire, surrounded by a layer of dielectric insulation, surrounded by a braided metal shield. These layers are made of completely dissimilar materials.
Like copper and Teflon, right?
Yes. Now imagine the test starts. The shaker table is roaring, the structure is vibrating violently, but the technician left the cable completely loose, just draping from the sensor down to the floor. As the structure shakes, that cable whips around. It flexes, it bends, it twists.
And because it's bending, the layers inside the cable are physically rubbing against each other.
Yes, exactly. The friction between the dielectric insulation and the braided shielding physically strips electrons from one material and deposits them on the other. It generates a false static electrical charge. It is the exact same physics as rubbing a balloon on your hair to create static electricity, just happening on a microscopic level inside a wire.
But wait, the data acquisition system, the DAQ, only reads voltage, right? It doesn't know where the voltage came from.
Exactly.
So the GAQ sees this electrical charge from the friction and just assumes the piezoelectric crystal inside the sensor generated it. It reads it as a massive spike in structural vibration.
The DAQ is entirely blind to the source. A voltage spike from a shattered titanium bracket looks exactly the same as a voltage spike from a wiggling piece of Teflon. It all just looks like raw data. The engineer sees this incredible overload on the graph and assumes the part failed.
This is terrifying.
Yeah.
We're talking about highly advanced mathematical models being completely defeated by a floppy cable. How does a shop floor ensure this doesn't happen? Do we just mathematically filter it out?
You cannot reliably filter it out because the triboelectric noise often occurs in the exact same frequency bands as the actual physical vibration you were trying to measure.
Oh, wow. So you're just stuck with it.
Unless you fix it physically.
Yeah.
The fix relies entirely on physical hygiene on the shop floor. First, to combat the bracket and mounting issues, the technician must tap the installed transducer with a small tool before the test even begins.
Like literally just hitting it with a tiny hammer.
A very small tap, yes. This excites the local resonances. If you look at the real-time analyzer and see resonance spikes appearing that you know do not belong to the transducer's internal frequency, which, is listed on its calibration sheet, you instantly know you have a mounting compliance issue. You have to remount it.
And what about the cables? How do you stop the static electricity?
You manually move the cable while watching the screen. Just grab it and wiggle it back and forth. If moving the cable generates noise spikes on your monitor, the cable is compromised, or you are experiencing a severe triboelectric effect.
So you just toss it.
You either replace that cable entirely, or you implement rigorous tie-downs. A cable should never be twisted when connecting it to the transducer, because that preloads internal stress. And it must be securely taped or anchored to the structure so that the cable moves perfectly in phase with the structure, eliminating the internal flexing.
So if the cable moves with the metal, it doesn't bend, so it doesn't rub. It is a beautifully simple physical fix for what looks like an impenetrable mathematical anomaly.
It really is.
But so far, we are just talking about temporary sensors. You bolt them on, you run the test, you take them off. What happens when the engineer needs permanent data? What happens when they specify an electrical resistance strain gauge that has to be physically glued to an airplane wing that is going to fly through freezing altitudes and scorching deserts? That introduces an entirely new tier of physical sabotage, doesn't it?
Oh, absolutely. The strain gauge is arguably the greatest friction point between the design engineer and the shop floor. Engineers treat strain gauges like magic data portals.
Magic data portals. I love that.
It's true. They provide incredible direct insight into the localized stress a part is experiencing. But technicians know that a strain gauge is essentially an incredibly fragile, temperamental science experiment that has to be conducted on a dirty workbench.
Okay, before we talk about how they fail, I want to make sure I truly understand how they work. My understanding is that a strain gauge is basically an impossibly thin piece of metal foil, usually some specific alloy attached to a very thin plastic backing. You glue the backing to your structure. When the structure bends or stretches, the foil stretches with it.
That is the mechanical premise, but the data actually comes from the electrical properties of that foil. As you stretch a piece of wire, two things happen. It gets longer and its cross-sectional area gets thinner.
Like stretching a rubber band.
Exactly like that. And both of those geometric changes make it more difficult for electrons to flow through the metal. Therefore, its electrical resistance increases. If the structure compresses, the wire gets shorter and fatter, and the resistance decreases.
Okay, I follow you.
So we run a small current through the foil, measure that microscopic change in resistance, and use it to calculate the exact physical strain of the part.
It is an elegant concept. But the sources highlight that this entire chain of logic rests on one microscopic vulnerability, right? The glue.
Yes. The chemical cleanliness and integrity of the bond. If you have a sensor that is measuring physical deformation at the micro-inch level, the transfer of that deformation from the heavy metal structure through the layer of adhesive, through the plastic backing, and into the foil must be absolute. It must be perfect.
But the shop floor is not a semiconductor clean room. What happens if a technician who, has been working on hydraulic lines all morning accidentally leaves a microscopic smudge of oil from their fingerprint on the metal before applying the epoxy?
The adhesive will not bond properly at that specific microscopic location. When the massive metal structure stretches, the foil sitting directly above that fingerprint smudge does not stretch. It simply floats over the gap.
Wow, just from a fingerprint.
Just a fingerprint. The resistance change is stunted. The engineer's computer receives a reading that the stress is well within safe limits, when in reality, the structure might be yielding and moments away from catastrophic failure. The math is completely blind to the fingerprint.
That is the scary part. The DDAU doesn't flash a warning light that says bad clue. It just gives you a lower number. But let's say the technician is flawless. They use chemical solvents, they prep the surface perfectly, the bond is molecularly pristine. The sources still indicate we're walking into a massive analytical trap called apparent strain.
I need you to explain this to me because it sounds like the material itself starts lying.
It does start lying. Apparent strain is a brilliant illustration of why an engineer cannot just look at a spreadsheet. They must understand the physical environment of the real world.
Okay, give me an example.
Let's imagine you perfectly bond a strain gauge to an aluminum beam. You leave it sitting on a bench in a laboratory. The air conditioning kicks off over the weekend, and the temperature in the room rises by 30 degrees. Okay, no forces are being applied to the beam, it's just sitting there getting warm.
Correct. But if you look at your data acquisition system, it will show a massive amount of mechanical strain. It will look like an invisible giant is trying to pull the beam apart.
Wait, because the metal changes electrical resistance when it gets hot.
That is half the problem. The thermal coefficient of resistance of the foil changes, yes. But more importantly, the aluminum beam undergoes thermal expansion. As it gets hot, the beam physically grows. Because the strain gauge is perfectly bonded to the beam, the foil is forced to stretch along with the expanding aluminum.
So the foil is physically stretching, and its resistance is changing due to heat, all without anyone touching it.
Yes. The DAQ measures this massive change in resistance and blindly converts it into mechanical stress data. It cannot distinguish between a hydraulic press is stretching me and I am sitting in a hot room. This is apparent strain. It is a completely phantom load.
So if I am an engineer designing a structural test for a jet engine casing where temperature is going to fluctuate wildly, how on earth do I design around that? If the heat is creating fake strain, my data is completely useless.
You solve it through meticulous material selection of the foil alloy, and this is where engineers often make critical errors by specifying the wrong gauge entirely. There are two primary alloys used in strain gauges, and they serve entirely different thermodynamic purposes: constant tan and isoelastic.
Okay, let's break those down. Why would I use constant tan?
Constant tan is an alloy specifically formulated to have a relatively flat thermal response curve. It is self-temperature compensating to a degree. If you are doing a static load test, meaning you are piling weights onto a wing and leaving them there for 3 weeks to see if it slowly bends, the temperature in the hangar is going to change between day and night.
Right.
You must specify a constant tan gauge because you need the alloy to resist changing its properties due to those ambient temperature fluctuations.
That makes perfect sense. But what is isoelastic? Why not just use constant tan for everything if it ignores temperature?
Because constant tan has a relatively low gauge factor. It doesn't produce a massive change in resistance for a tiny amount of strain. It is not incredibly sensitive. Isoelastic alloys, on the other hand, are highly sensitive. They produce a huge, easily readable signal. But the trade-off is that isoelastic is wildly sensitive to temperature. The slightest thermal shift will create massive apparent strain.
So why does it even exist? It sounds like a total liability.
It is designed exclusively for dynamic shock events. Let's say you are testing a ballistic impact or a massive pyroshock event. The entire mechanical event occurs in 2 milliseconds. You need the extreme sensitivity of the isoelastic gauge to capture that incredibly rapid, fleeting spike in strain.
And because it's so fast, the temperature doesn't matter.
Exactly. Because the event only lasts 2 milliseconds, the ambient temperature does not have time to change. The thermal instability of the alloy is totally irrelevant because the timescale is too fast for heat transfer to occur.
Let me stop you right there. I see the trap. If a design engineer just looks at a catalog and says, oh, this isoelastic gauge has a much stronger signal output, I'll specify that one for my 3-month structural fatigue test.
Oh, it's a disaster. They will end up painstakingly measuring the cyclic performance of the laboratory's HVAC system rather than the fatigue of their aerospace part.
That's hilarious and terrible.
The data will just be this rolling wave of apparent strain that completely obscures the tiny mechanical fatigue cycles.
And the technician on the floor probably knows this. The technician sees the work order specifying an isoelastic gauge for a static test.
Yeah.
And they know the data will be garbage. But the specification is the law.
Yep. They just follow the blueprint.
And that brings us to another geometric trap hidden inside the strain gauge: transverse sensitivity. I have looked at these things under a microscope. The foil isn't just a straight line. It is patterned into a grid. It winds back and forth like a hairpin road ascending a steep mountain.
Yeah.
Why do we do that, and how does it ruin the data?
Well, the foil's incredibly thin, but we need the electrical path to be very long. To get a measurable starting resistance, say 120 or 350 ohms, you need a lot of wire. If you just used a straight wire, the strain gauge would be a foot long. To compress all that wire into a footprint the size of a postage stamp, we etch the foil into a serpentine grid, a series of long vertical lines connected at the top and bottom by tiny horizontal loops.
Right, the hairpin turns.
Exactly. You mount the gauge so the long vertical lines are pointing in the direction of the strain you want to measure. When the part stretches longitudinally, those long lines stretch and you get your data. But here's the fatal flaw: the tiny horizontal loops at the ends of the grid. Because those segments of foil are traveling sideways transversely, they will stretch and change resistance if the metal beneath them stretches sideways.
I think I see the problem. If I put a heavy load on a block of rubber, it squishes down. But it also bulges out the sides. Metal does the same thing, just on a microscopic scale, right? Poisson's ratio.
Yes. When you stretch a piece of metal lengthwise, it simultaneously contracts across its width. The transverse loops on the strain gauge pick up that lateral contraction and alter the total electrical resistance of the grid. The gauge accidentally reads strain from a direction you did not intend to measure.
So a portion of my signal is contaminated by transverse motion. If the engineer doesn't know the exact transverse sensitivity coefficient of that specific gauge batch, they might be overestimating or underestimating the primary longitudinal stress. We're building a massive tower of assumptions here.
And that is the reality of the physical disconnect. The math is only as solid as the cleanliness of the technician's hands, the thermal foresight of the engineer, and the geometry of a microscopic loop of foil.
Okay, let's say a miracle occurs. The shop floor executes flawlessly. The brackets are stiff, the cables are anchored, the strain gauges are perfectly bonded with the exact right alloy, and the room temperature is locked in tight. The physical setup is immaculate. The raw data, pure, unadulterated voltage, now flow through the wires into the engineer's computer. The physical pain is over.
And the digital pain immediately begins.
Awesome.
Welcome to the data processing minefield. This is where an entirely new set of brutal misconceptions lives, because taking continuous analog voltage and forcing it into a digital spreadsheet requires mathematical compromises.
I want to start with what the sources call out as the apex predator of condition monitoring mistakes. It is a misconception so common that it literally dictates how entire factories are run. The overall level misconception. Break this down for me.
This is a pervasive systemic issue when monitoring the health of operating machinery. Humans have a deep-seated psychological desire to simplify complex data. If you have a massive industrial compressor running in a factory, management does not want to look at a swirling three-dimensional waterfall plot of frequency spectra.
They just want a green light or a red light.
Exactly. They want a single, easily digestible number on a dashboard. They want to boil the entire health of a complex machine down to an overall vibration level.
Right. If the overall vibration goes above a certain threshold, the alarm sounds. It seems incredibly logical. More vibration means more damage.
It seems logical, but it is a catastrophic trap. The sources give a fantastic example of why this fails. Relying on an overall root mean square measurement of vibration often results in totally incorrect predictions, almost always wildly overestimating the amount of lead time you have before a machine tears itself apart.
Wait, why does it overestimate the time? Why doesn't the overall level spike when a bearing starts to fail?
Because of the massive disparity in energy between low-frequency motion and high-frequency motion. Let me give you an analogy. Imagine you are trying to listen for the faint, high-pitched whine of a single mosquito, but you are standing inside a room with a roaring, low-frequency jet engine.
Okay, the jet engine completely dominates the acoustic energy in the room.
Yes. If you have a decibel meter, an overall sound level meter, it will read a massive number, say 120 decibels, generated entirely by the jet engine. Now let's say the mosquito gets 10 times louder. Will your overall decibel meter change?
Not a bit. The mosquito's energy is a rounding error compared to the roar of the engine.
That is exactly what happens in machinery. The heavy, rotating mass of the shaft, the unbalance of the rotors, the normal pulsing of the fluids, these generate a massive low-frequency wave that dominates the overall vibration level. A failing rolling element bearing, however, produces tiny, sharp, high-frequency impacts as the cracked steel balls roll over a pit in the raceway.
Ah, I see.
The energy contained in that high-frequency click is microscopic compared to the low-frequency hum of the machine.
So the bearing could be grinding itself into metallic dust, sending out thousands of tiny, high-frequency shock waves, and the overall vibration average won't even twitch.
The overall level will not shift enough to trigger an alarm until the bearing completely seizes, the shaft drops, and the machine physically breaks itself apart. You get no early warning. By the time the overall level spikes, it is no longer a warning, it is a postmortem.
Wow, so how does an engineer actually catch the mosquito? How do we find that bearing defect before the machine destroys itself?
You must abandon the overall level entirely and rely on specific frequency spectra. The data acquisition system takes the complex time waveform and runs it through a fast Fourier transform and FFT. This algorithm breaks the chaotic wave down into its individual frequency components. It separates the jet engine from the mosquito.
It creates a graph where the horizontal axis is frequency and the vertical axis is amplitude.
Correct. You then compare that specific spectrum against a baseline reference spectrum that was taken when the machine was brand new and healthy. You are no longer looking for an overall increase. You are looking for highly specific, localized tells. Fingerprints of failure.
What does a fingerprint of failure look like on a frequency graph?
Let's say you see a sharp spike in vibration appearing at exactly 2 times the running speed, or the RPM, of the shaft. That is a classic signature of mechanical looseness.
Like the bolts are rattling.
Yeah, maybe the mounting bolts on the base plate are backing out. The unbalance of the shaft hits the loose footing twice per rotation, generating a spike at 2 times the RPM. If you see discrete spikes at exactly 1, 2, 3, and 4 times the RPM of a belt drive, you are likely looking at a faulty, worn belt slapping the sheaves. You diagnose the machine by looking at the specific frequencies where the energy is hiding.
That is incredibly elegant. But to get those beautiful diagnostic frequency spectra, the analog voltage signal from the sensor has to be digitized with a DAQ.
Yeah.
It has to be chopped up into discrete numbers. And the sources detail 2 massive signal processing pain points that occur during this analog to digital conversion: aliasing and leakage.
Both absolute nightmares.
I want to spend some time on aliasing because the math behind it feels almost deceptive.
Aliasing is perhaps the most insidious error in digital signal processing because if it happens, the computer doesn't crash. It doesn't give you an error code. It simply lies to you with absolute mathematical confidence. Aliasing occurs if your sampling rate, the speed at which the computer takes snapshots of the incoming voltage, is not fast enough to capture the true physical frequency of the vibration.
The sources mention the Nyquist frequency limit, and here's where I want to challenge the standard textbook explanation. The text says F sub A equals 1 divided by 2 times delta t being the time between digital samples. That formula means nothing to me physically. I need to visualize why the math breaks down.
Let's visualize it without the formula. To accurately capture the shape of any wave, the absolute minimum requirement is that you must take a sample at least twice per cycle. You need to catch the peak of the wave and the valley of the wave. If a wave is vibrating at 100 hertz, 100 cycles per second, your computer must take at least 200 samples per second to see it. That is the Nyquist limit.
What happens if I don't? What happens if a high-frequency vibration sneaks into my sensor, say a vibration at 400 hertz, but my computer is only taking snapshots at 100 times a second?
The digital system cannot accurately represent that fast 400 hertz wave. It doesn't have enough snapshots. But the computer has to draw a line connecting the snapshots it did take. Because the high-frequency wave is oscillating so rapidly between the slow snapshots, the computer draws a smooth line connecting the dots that happens to form a completely false, low-frequency wave. The high frequencies physically fold back into the data.
I'm trying to think of a physical analogy for this. It's like standing in a windowless room, trying to figure out how fast ocean waves are crashing against a pier. But you're only allowed to open a small window and look outside for a split second once every 10 seconds.
That is a phenomenal analogy. Let's play that out.
If the real ocean waves are crashing fast, say, a new wave hits the pier every single second, but I only open my window every 10 seconds, I might accidentally look out right as a wave is hitting the pier. 10 seconds later, I look out again, and I happen to catch another wave hitting the pier. I close the window and write down, the ocean is very calm. 1 wave hits the pier every 10 seconds.
And you have constructed a perfectly logical, mathematically sound conclusion based on your data. But your data is a hallucination. The high-frequency waves have aliased into a false, low-frequency observation.
And the most common visual example of this is the wagon wheel effect in movies, right?
Yeah.
You are watching a movie of a car accelerating, the wheel is spinning faster and faster. Suddenly, the spokes seem to freeze, and then they start spinning backward even though the car is going forward.
Yes, exactly. The movie camera is taking a snapshot 24 times a second. As the wheel spins faster, it eventually rotates so far between frames that the next spoke moves into a position slightly behind where the previous spoke used to be. The camera connects the dots, and your brain perceives a slow backward rotation. That backward rotation is an aliased frequency.
So if a design engineer gets alias vibration data, they might see a massive low-frequency resonant spike on their graph. They might spend months redesigning the heavy structural supports of their machine to eliminate a low-frequency hum.
A hum that does not physically exist. The actual problem was a high-frequency vibration from a gear mesh that aliased downward. They are trying to solve a ghost in the machine.
That's insane. So how do you prevent it? Do you just buy a faster computer?
You cannot solve it digitally. Once a signal is aliased in the digital domain, it is mathematically impossible to separate the fake low frequencies from the real low frequencies.
Yeah.
It is baked in. The only way to prevent it is in the analog physical world.
So what do you do?
You must pass the raw analog voltage through a physical hardware low-pass filter before it hits the digital converter. The filter physically scrubs away any frequencies higher than your Nyquist limit, ensuring they cannot enter the computer and cause havoc.
You literally have to put a bouncer at the door of the computer to keep the fast waves out. I love that. Now, what about the second signal processing trap? Leakage. This one sounds messy.
Leakage is an artifact of the fast Fourier transform algorithm itself. The mathematics of the FFT assume that the chunk of time you are analyzing the sample record is a perfectly periodic signal that loops infinitely.
Meaning the waves you recorded perfectly repeats forever.
Yes. For the math to work perfectly, your sample record must capture a complete whole integer number of cycles of the vibration wave. It must capture exactly 5 full waves, or exactly 50 full waves. It has to start at 0 and end at 0.
But in the real world, you were just hitting the record button for an arbitrary amount of time. You might accidentally capture 5.5 waves. You chop the wave off mid-cycle.
And when you chop a wave off mid-cycle, the FFT algorithm panics. The sharp discontinuity at the end of the recording violates the mathematical assumption of continuity. As a result, the algorithm cannot pinpoint the exact frequency. The energy from that sharp, precise frequency literally leaks out into the adjacent frequency bins on the graph.
So a beautiful, needle-sharp resonance spike at exactly 120 hertz suddenly smears out. It looks like a broad, sloping mound of vibration energy covering everything from 110 to 130 hertz.
Exactly. The engineer looks at the leaked data and thinks they have a broad, sloppy resonance problem affecting a wide band of frequencies, when in reality it is a highly tuned, very specific single-frequency issue. They might specify massive amounts of damping material to try to absorb that broad amount of energy, adding completely unnecessary weight and cost to the part.
To fix it, you use a windowing function, right? The software artificially forces the edges of your chopped recording down to 0 to smooth out the transition.
Yes, a Hanning window is the most common. It gently tapers the beginning and end of the recording to 0, suppressing the leakage effect at the cost of slightly reducing the overall amplitude accuracy. It is a necessary mathematical compromise.
Okay, let's step back and survey the battlefield. The design engineer has navigated the mass loading, the temperature shifts, the aliasing, and the leakage. They have pure, accurate data. They design the part based on this flawless data.
Yeah.
Now, the finished prototype goes back down to the shop floor for qualification testing, the final exam. It is time to put the prototype on a massive shaker table or a drop table and subject it to the ultimate physical stress to see if it survives before they put it in a rocket.
And this is where the theoretical and the physical worlds often clash most violently, because perfectly simulating a complex real-world service environment inside a laboratory is incredibly difficult. And the methodologies engineers use to bridge that gap are plagued by outdated, deeply destructive myths.
The largest, most pervasive myth detailed in the sources is the equivalent damage concept. This is the idea that you can simulate a complex, multi-layered, random vibration environment by just taking the part, putting it on a shaker table, and hitting it with a really hard, pure sine wave for a short period of time.
It is a fundamentally flawed, archaic concept that refuses to die because it is cheap and easy to program into a shaker table. Let's contrast the two environments. In the real world, equipment experiences random vibration. Think of a truck driving over a rutted dirt road, or the aerodynamic buffeting on the skin of an aircraft. Random vibration contains energy at all frequencies simultaneously, constantly shifting in amplitude.
It's broadband noise, like static on a television.
Exactly. When you expose a structure to random vibration, it excites multiple structural modes simultaneously. The wings flap, the fuselage twists, the panels bow all at the same time. These different modes interact with each other. Stresses combine in complex, unpredictable ways.
And a sine wave test is the exact opposite of that.
A sine wave test is a pure single frequency sweeping slowly up the spectrum. It is like hitting a tuning fork. The equivalent damage myth assumes that you can mathematically equate the fatigue damage caused by thousands of hours of complex random vibration to a short burst of intense single-frequency sine vibration.
We know it's going to experience 10 years of random rattling in the truck, so let's just shake it incredibly hard at 50 hertz for 2 hours and call it even. Why does that damage model fail?
Because fatigue is not linear, and structural interaction is critical. When the shaker hits the structure with a hard sine wave at its primary resonance frequency, it excites that single mode violently, far beyond what it would ever experience in the real world. This usually results in a severe overtest. The part tears itself apart in the lab from a single axis stress that would never occur in isolation in the field.
So you throw away a perfectly good design because the test was artificially harsh.
Or, conversely, you severely undertest the equipment. A sine wave sweep only spends a few seconds at any given frequency. If the part has a critical vulnerability that requires time to fatigue, the sine wave sweeps right past it before the crack can propagate. The weak design passes the test, goes into the field, and fails catastrophically 3 months later. Whenever physically possible, you must simulate random vibration with random vibration testing. You cannot take shortcuts with physics.
The random vibration is just shaking. It gets even crazier when we talk about shock testing sudden violent impacts. Let's break down a massive real-world mistake detailed in the sources, attempting to use a standard drop table to simulate a pyroshock.
Oh, this is a classic, deeply misunderstood area of testing. It stems from engineers treating the word shock as a universal constant. A shock is not just a shock. The energy profile matters immensely. Let's define the two events. A standard drop table test is used to simulate a velocity shock. You bolt the equipment to a heavy carriage, raise it in the air, and drop it onto a specialized anvil.
It is the exact physical simulation of a warehouse worker accidentally dropping a television out of the back of a delivery truck. The TV is falling at high speed, and then in a fraction of a millisecond, it hits the concrete. The velocity goes from 30 miles an hour to absolute zero instantly. A massive sudden velocity change.
Exactly. That massive velocity change generates a tremendous amount of low-frequency energy. The heavy structural frame of the TV has to absorb all of that kinetic energy, which causes the frame to yield, bend, or snap. Now, consider a pyroshock.
An explosive event.
Yes. A pyroshock occurs when an explosive device is detonated directly on or near the structure. A common aerospace example is an explosive bolt firing to separate two stages of a rocket in space. When the explosive detonates, it creates an incredibly intense, localized shock wave of extreme high-frequency energy that ripples through the metallic skid of the rocket.
And this is the crucial difference to me. There is almost no net velocity change. The rocket doesn't suddenly stop moving. It is still cruising through space at Mach 10. The structural frame doesn't experience a massive shift in momentum.
Precisely. The heavy structural members of the rocket, the thick beams and trusses, are physically too massive to respond to high-frequency energy. They act as low-pass filters. The shock wave simply passes through them without causing them to significantly flex or bend. A pyroshock rarely damages heavy structural components.
So what does a pyroshock destroy?
It is deadly to delicate high-frequency components. The intense high-frequency energy resonates the tiny elements inside microchips, it shatters delicate electrical relays, and it fractures microscopic solder joints on circuit boards.
Okay, so let's set the trap. A design engineer looks at a specification sheet. The sheet says the new satellite component must survive a pyroshock event, generating a peak acceleration of 2,000 Gs. The engineer sends the component down to the shop floor and says, the spec says 2,000 Gs, put it on the drop table and drop it until it hits 2,000 Gs. What happens?
It is an absolute disaster. The technician raises the drop table carriage to the ceiling and drops it. To generate a 2,000 G peak on a drop table, you have to induce an astronomical velocity change. When the carriage hits the anvil, it unleashes a colossal tidal wave of low-frequency energy into the component.
The television hitting the concrete.
Yes, and because it is low-frequency energy, the heavy structural members of the satellite component respond violently. The brackets snap. The thick titanium beams warp and shear in half. The entire assembly is reduced to twisted metal.
The engineer comes down, sees the wreckage, and assumes their design was incredibly weak. They spend months beefing up the titanium, adding weight to a satellite where every ounce costs $10,000 to launch.
And the tragic irony is that the original lightweight structure would have survived the actual explosive pyroshock in space without a single scratch. Forcing a drop table to simulate a pyroshock forces a massive low-frequency structural failure that would never, ever happen in the real world. The test environment becomes the destructive agent, not the service environment.
It's like testing a submarine's ability to survive water pressure by dropping a bank safe on it. You are applying the wrong kind of force. And this friction between the equipment and the test machine leads us to another fascinating phenomenon detailed in the text: equipment structure interactions. This is where the physical reality of the test bench fights back against the digital controller.
If we connect this to the bigger picture, we have to realize that a shaker table is not an infinite, unstoppable force of nature. It is a machine with physical limits. When the shop floor mounts a massive, heavy piece of equipment to a shaker table, the equipment itself becomes an active participant in the physics of the table.
The sources refer to this as the dynamic absorber problem.
Yes. Let's say you are testing a massive 500-pound electrical generator. The generator has its own internal resonant frequencies. The shaker table begins its sweep, increasing in frequency. When the shaker hits one of the generator's internal resonant frequencies, the internal components of the generator begin to oscillate wildly.
The mass inside the generator starts moving in opposition to the table.
Exactly. The resonating mass of the generator acts as a dynamic vibration absorber. It essentially sucks the kinetic energy right out of the shaker table. The generator is physically fighting to hold the table still.
The part is screaming at the test machine, "No, I am vibrating now. You stop moving."
That is precisely the physical interaction. But remember, the shaker table is being driven by a digital control loop. The computer has a strict mathematical profile it must follow. Maintain an acceleration of 5 Gs at all costs. When the generator absorbs the energy, the accelerometers on the table detect a sudden, massive drop in motion. The table is no longer hitting 5 Gs.
Because the part is eating all the energy.
Yeah.
So what does the control computer do?
The control system panics. It sees the dip in acceleration, assumes it is not pushing hard enough, and commands the hydraulic amplifiers to pump massive, extreme amounts of force into the table to push through the resistance and force the table back up to the specified motion curve.
And what happens to our 500-pound generator?
It gets absolutely hammered. The input faint spikes to destructive levels, and the generator is subjected to a severe overtest at the exact frequency where it is most vulnerable.
Let's compare that to reality. If that generator was bolted to the wing of an airplane and it started resonating and absorbing energy, the wing wouldn't suddenly summon infinite hydraulic power to fight back, right?
Exactly. The airplane wing is flexible, it yields. When the generator resonates, the wing allows the local vibration level to dip. The structure and the equipment negotiate the energy transfer, but the shaker table's control loop refuses to negotiate. It acts like an infinitely stiff, infinitely powerful wall.
It bullies the part to death. So what is the fix? How do we program the shaker table to act more like a flexible airplane wing and less like an unyielding tyrant?
The solution is a technique called dual control testing. Instead of giving the shaker table a single absolute mandate, maintain this acceleration motion at all costs, you place intelligent limits on both the input motion and the input force. You give the control loop 2 sensors, an accelerometer to measure motion, and a force transducer to measure the physical effort being exerted.
A dual feedback loop.
Yes. You tell the system, try to achieve the requested 5 Gs of motion, but if the physical force required to achieve that motion exceeds a realistic pre-calculated limit, pull back. Do not exceed the force limit. This allows the table to temporarily dip below the required motion when the equipment resonates, perfectly mimicking the natural yielding of a real-world flexible foundation. It prevents the catastrophic overtest.
It introduces empathy into the digital control loop. It respects the physics of both the part and the environment. I love that. Now, let's pivot and look at this from the other side of the chasm. How can the design engineer sitting at their CAD workstation design the system right the first time so the shop floor isn't forced to run impossible tests or build assemblies that are doomed from the moment they are bolted together? Let's talk about designing for survival.
The most common pitfall originating in the design department is the psychological trap of overspecification. It stems from a very human, well-intentioned desire to be safe, to build in a margin of error.
The classic engineering safety factor. If the bridge needs to hold 10 tons, build it to hold 30 tons.
Exactly. An engineer looks at the flight data and sees that the service environment will expose the electronic equipment to a maximum of 1 G of vibration. They want to ensure it survives, so they write the formal specification demanding that the equipment be designed and tested to withstand 2 Gs. Double the requirement, double the safety.
It sounds perfectly logical.
It sounds logical, but it completely ruins shock and vibration isolation systems. Isolators like rubber elastomer mounts, wire rope coils, or pneumatic springs are highly tuned, highly nonlinear dynamic systems. You do not just buy generic rubber, you select the specific stiffness of the isolator based entirely on the exact load and the exact deflection it needs to handle.
Let's follow the math. If the engineer artificially doubles the specification to 2 Gs, they must mathematically assume the forces involved are twice as high.
Yes. And to handle those imaginary heavier forces without the equipment crashing into the surrounding bulkheads, the engineer is forced to specify an isolator that is physically much stiffer.
So they buy a very hard, rigid piece of rubber instead of a soft, compliant piece of rubber.
Correct. Now, the equipment is built with these ultra-stiff isolators, and it is put into the real world, but the real world only delivers 1 G of vibration. The actual force is half of what the isolator was designed to handle.
So what happens to the stiff rubber?
It barely moves. It requires 2 Gs of force to compress it, so the 1 G environment cannot overcome its stiffness. Because it does not deflect, it does not isolate the kinetic energy. It acts like a solid metal block, transmitting the high-frequency shock and vibration directly into the fragile electronics it was supposed to protect. By trying to be overly safe on paper, the engineer practically guaranteed a structural failure in reality.
The desire for a safety margin actually destroyed the safety mechanism. The sources provide a very specific, hard geometric rule of thumb for this when dealing with elastomeric or rubber compression isolators. It isn't just about the stiffness, it's about the shape of the rubber changing under load.
Yes. When you compress a block of rubber, the volume doesn't change. The material just displaces sideways. It bulges. The text dictates that to ensure the rubber actually isolates dynamically and doesn't just turn into a rigid rock under sudden impacts, the ratio of the static deflection, how much it swishes just from the weight of the equipment to the original uncompressed thickness of the rubber, should never exceed 0.15.
So a maximum of 15% compression. Why is that specific number so critical?
If you compress the rubber past that 15% mark, it bulges too much outward. The internal geometric stresses change, and the rubber dramatically stiffens in its dynamic response. It might feel soft when you push it slowly, but when a high-speed shock wave hits it, that highly bulged rubber acts almost like steel. It loses its isolating magic.
It bottoms out dynamically, even if it hasn't bottomed out physically. That is a brilliant piece of structural insight. And speaking of geometric rules, there is another rule in the text that feels like a cheat code for CAD designers. It is the center of gravity rule for isolator placement.
This is perhaps the most vital geometric rule for ensuring an isolation system works predictably. When you mount a delicate piece of equipment, say a laser targeting system on a set of 4 isolators, you want the entire system to move linearly when a shock hits. You want the box to bounce straight up and down, or shift perfectly straight side to side. You want translation.
Right, like a car riding smoothly over a bump, the whole chassis goes up and down evenly.
Exactly. What you desperately want to avoid are rocking modes. A rocking mode occurs when the equipment twists, rotates, and pitches on the mounts. One side goes up while the other side goes down.
Why are rocking modes so bad?
Because they are incredibly complex to damp out, they couple lateral and vertical vibrations together chaotically, and they place huge, uneven tearing stresses on the isolators themselves, drastically shortening their lifespan.
So how does the engineer sitting at their computer screen prevent the box from rocking?
By mathematically aligning the geometry of the mounts with the center of gravity. The rule is strictly defined. The vertical distance between the horizontal plane of the isolators and the center of gravity of the equipment must be equal to or less than 1/3 of the minimum horizontal spacing between the isolators.
Let me visualize that to make sure the math translates to reality. Imagine I am designing a square metal box, and I'm putting a rubber mount on each of the 4 bottom corners. If those 4 rubber mounts are spaced exactly 12 inches apart from each other horizontally,
Then you take that 12 inches divided by 3, and you get 4 inches. The center of gravity of your metal box, the heavy core where all the mass is concentrated, cannot be higher than 4 inches above the plane of those rubber mounts.
if the center of gravity is 5 or 6 inches high, what happens?
The box becomes dynamically unstable. It acts like an inverted pendulum. The mass is too high relative to the base. When a horizontal vibration hits the base, the high center of gravity creates a massive moment arm, and the box immediately wants to tip over and rock.
And the beauty of this is that the engineer can fix this problem entirely in CAD before a single piece of metal is cut. If the center of gravity is too high, they don't need complex active damping systems or crazy spring rates. They just redesign the brackets to lower the attachment points, or they widen the stance of the mounts from 12 inches to 18 inches.
Exactly. By simply dragging a mounting bracket 3 inches wider on a computer screen, the engineer completely eliminates a dynamic, chaotic nightmare that the shop floor would have spent weeks and thousands of dollars trying to damp out physically. It is the perfect example of bridging the gap, using the theoretical geometry to solve a physical reality.
It's amazing how a few pixels on a screen translates to surviving a real-world shock test. As we work toward the end of this incredibly dense material, I want to pivot slightly. We've been looking at this from a high-level systemic perspective, but the sources also contain a wealth of granular practical knowledge. I want to weave in some of the most common fundamental questions that practitioners, both engineers and technicians, are constantly asking when they try to implement these rules. Let's start with a foundational measurement problem that I kept tripping over while reading.
Let's hear it.
The shop floor technician is staring at a massive, vibrating industrial fan. They have a data acquisition system that is capable of converting the raw voltage into 3 different mathematical parameters: displacement, velocity, or acceleration. Displacement is how far it moves, velocity is how fast it moves, acceleration is the rate of change of that speed. Which parameter should they actually tell the computer to measure and display? Does it even matter, since they are all mathematically related?
It matters immensely from an instrumentation and analysis standpoint, and the choice is dictated by what we call the flattest spectrum rule.
The flattest spectrum rule. Explain that concept.
Let's assume you are measuring a complex machine that is generating vibration across a huge range of frequencies, from 10 hertz up to 10,000 hertz. You want your plotted data graph to be relatively uniform, relatively flat across that entire frequency band.
Why do I want it flat? Why do I want huge spikes on one end and tiny microscopic ripples on the other?
Because of the dynamic range limitations of your sensors and your analog to digital converters, if your data has massive, towering, low-frequency peaks and incredibly tiny, high-frequency peaks, the computer has to scale its graph to fit the massive peaks. When it scales up to fit the giants, the tiny, high-frequency details shrink down into the mathematical noise floor and become completely invisible. A flat spectrum ensures that an anomaly at 20 Hz is just as visible and requires the same instrument resolution as an anomaly at 8,000 Hz. It balances the picture.
Okay, that makes perfect logical sense.
Okay.
Back to the fan. Which parameter gives me the flat picture?
For the vast majority of rotating machinery, pumps, fans, motors, gearboxes, velocity is the parameter that provides the flattest overall spectrum. Displacement heavily biases low frequencies. A displacement graph of a machine will show massive mountains at the low end and practically nothing at the high end. Acceleration does the opposite. An acceleration graph will look like a flat line at the low end and explode into massive spikes at the high end.
But velocity sits comfortably in the middle, pulling down the low-frequency mountains and lifting up the high-frequency spikes.
Precisely. Velocity gives you a roughly uniform landscape, meaning an increase in vibration at any frequency has an equal chance of being spotted by the technician. It is the gold standard for general machinery health monitoring.
That leads me directly into my next question, which involves a massive physical roadblock. The technician has their velocity sensor. They place it on the bearing housing of a critical milling machine. But that milling machine isn't floating in space. It is bolted tightly to a concrete factory floor. And 30 feet away, a massive stamping press is slamming down every 3 seconds, sending shockwaves through that shared floor. If the sensor is on the milling machine, how on earth do you know if the vibration you are recording is actually a failing bearing in the mill, or just the stamping press vibrating the floor? How do you separate the machine from its environment?
That is one of the most complex challenges in physical acoustics, separating the source vibration from the transmission path vibration. Because in a normal time waveform signal, just watching the squiggly line on an oscilloscope, those two elements are deeply convolved.
Convolved, meaning they're multiplied and tangled together mathematically. They're baked into a single cake, and you cannot easily separate the flour from the sugar.
Exactly. The vibration of the mill and the vibration of the floor interact, amplify, and cancel each other out in the time domain. But there is a highly specific, very powerful mathematical tool designed to untangle this knot: cepstrum analysis.
Cepstrum. C-E-P-S-T-R-U-M. Sounds like an anagram of spectrum.
It is an anagram of spectrum, and that is a deliberate joke by the mathematicians who invented it. The cepstrum is literally the inverse Fourier transform of the logarithm of the power spectrum. It is a spectrum of a spectrum.
A spectrum of a spectrum. Okay, my brain is starting to melt. I don't need to do the math by hand, but physically, what does taking the cepstrum actually achieve? Why does it untangle the cake?
The magic lies in the logarithm step. In the normal time signal, as we discussed, the source effects and the path effects are convolved. They are multiplied together. But when you take the logarithm of the spectrum, mathematical properties dictate that multiplied terms become added terms.
Oh, wow. So instead of a tangled multiplication problem, it becomes a simple addition problem, A plus B.
Exactly. And when you perform the final transform to create the cepstrum graph, the different physical characteristics separate into entirely different physical regions on the plot. The effects of the source, the sharp repeating harmonics of the milling machine's gears, cluster into highly specific, localized peaks called harmonics.
Another anagram, harmonics instead of harmonics.
Yes. Meanwhile, the effects of the transmission path, the broad, resonant echo of the concrete floor, stretch out into completely different, wide regions of the graph. You can literally draw a vertical line down the middle of the substrum plot. You look at one side to analyze the gears in the machine, and you look at the other side to analyze the resonance of the factory floor. The math forcibly separates the machine from the environment.
That is essentially computational magic. It allows the engineer sitting 1,000 miles away to mathematically isolate a single piece of metal in a chaotic factory. Okay, final roadblock. Let's move away from monitoring and back to testing. I am looking at two different test specifications in the sources, a durability test and a functional test. To a layman, a test is a test. Put it on the shaker and shake it. What is the actual physical difference between these two paradigms?
It entirely comes down to what specific category of physical failure the engineer is hunting for. The testing philosophies are diametrically opposed. A durability test is designed to find hard failures.
Define a hard failure.
Physical, irreversible breakage. Metal fatigue. A structural beam cracking in half. A mounting bracket shearing its bolts off. The chassis permanently warping. These are structural failures that physically destroy the integrity of the part.
And the crucial element of a hard failure is that it is time dependent, right? You don't usually bend a piece of steel back and forth once and have it break.
Yeah.
It takes thousands or millions of cycles for the microscopic crack to propagate.
Exactly. Fatigue is a function of time and cycle accumulation. Because of this, durability tests are highly accelerated. An engineer cannot afford to put a car suspension on a shaker table and run it for 10 years to see if it lasts 10 years. So, we use the inverse power law of fatigue. We dramatically increase the amplitude of the vibration, shaking it much violently than it would ever experience in reality in order to compress 10 years of normal fatigue accumulation into a few hundred hours of testing in the lab.
So during a durability test, it is shaking violently. If the digital screen on the dashboard glitches out and resets during that violent shaking, does the engineer fail the test?
No, they do not care. The durability test is purely about the physical structure. The electronics are not expected to function normally under those artificially accelerated, exaggerated loads. As long as the dashboard doesn't physically snap off its mounts, the test is a success.
So that brings us to the functional test.
The functional test hunts for soft failures. These are transient, temporary failures that disrupt the operation of the equipment without physically breaking it. A delicate electrical relay chattering open for a millisecond. A laser optic momentarily vibrating out of alignment. A software glitch caused by signal noise.
And unlike metal fatigue, a soft failure isn't accumulating over time. It doesn't take 10 years for a relay to chatter. If the vibration is high enough, it chatters instantly.
Precisely. Soft failures are not time-dependent, they are amplitude-dependent. Therefore, you cannot accelerate a functional test. If you artificially increase the vibration amplitude, you will cause relays to chatter that would never ever chatter in the real world. You will induce fake failures.
So how do you run it?
You run the functional test at the exact maximum vibration level that the equipment is expected to encounter in its normal service environment, not a fraction of a G higher. And the mandate is absolute. The equipment must operate flawlessly, with full electrical and mechanical functionality during the entirety of the vibration exposure. The duration of the test doesn't really matter, it just has to work perfectly while it's shaking.
That distinction, accelerating to break the metal versus real-time levels to test the electronics, is so critical for avoiding the twin demons of over-testing and under-testing. We have covered an immense amount of ground today, traveling from the microscopic smudges under a strain gauge to the colossal low-frequency tidal waves of a drop table. As we wrap up this deep dive, I want to leave you with a final thought to mull over as you walk out onto the shop floor or sit down at your CAD terminal. We have talked extensively about the friction between the theoretical model and the physical reality. Consider how the very act of observing and isolating our physical world fundamentally alters it. We talk about this concept in quantum mechanics, with the observer effect, the idea that observing an electron changes its path. But we rarely acknowledge that we experience the exact same phenomenon on a greasy workbench. When you stick a heavy accelerometer to a thin beam, you're not measuring the beam. You are measuring a new system you just created. When you bolt a stiff isolator to a flexible airplane floor to protect a computer, the floor and the isolator engage in a physical argument over who have to absorb the energy. We are never just measuring or isolating a pure theoretical system in a vacuum. We're always inevitably interacting with it, The perfect design, the flawless frequency, the pure sine wave, these only exist on the mathematical paper. The real physical world is a relentless, chaotic, collaborative negotiation between the engineer's pristine math and the shop technician's physical reality.
It is a profound realization, and it raises an ultimate question for every design. Are you designing for the purity of the paper, or are you designing for the chaos of the negotiation? Because only one of those designs will survive the shaker table.
Victory belongs to those who refuse to lose. Thanks for riding with me, Design Junkies. Stay hungry. If this episode gave you even one solid takeaway, drop a comment. It takes you a few seconds, but it tells me this workbench is actually helping and worth keeping alive. We don't make a dime off this, and that's by design. As long as it's helping you get sharper, that's enough.